All right. Well, this lecture is coming super late, but we'll still cover it. Decision trees and random forests. So a decision tree is a classification or regression method, machine learning method, and it allows us to kind of make predictions based on our input variables. And the way it does that is it takes all of the observations in our training data and it splits them up into smaller chunks. And the way it splits it is it uses just one explanatory variable and it forms a binary split using some kind of simple rule. And this creates the branches on the tree. So if the explanatory variable is numeric, then the split's going to be kind of in the form of, is x greater than k, greater than or equal to k, or is x less than or equal to k? And so you just kind of split the data into two parts that way. If the variable that we're looking at is categorical, it's going to take the different categories and we'll say, all right, if you belong to categories A and B, you go down this side of the branch. If you belong to categories C and D, you go down that side of the branch. Okay. And what happens is this partitioning, splitting the data, continues until some kind of stopping criterion is reached. So in the beginning, all of your observations are just in kind of one partition, and then you split it into two, and then you take this portion, not necessarily half of the data, but the side that went down this portion, you split that again into two parts, and then you take each of those and you split those, and you just kind of keep going and going until you have some kind of stopping criterion, which will be either you've made this many splits or this many partitions have reached. And then, and so you have this one portion at the end, and the way the decision tree goes is that every single observation that fits that terminal node or that terminal leaf, we predict one single value, okay? And as far as the value that gets predicted, you can predict a numeric value, and that would be a regression tree, or you can predict a classification, a category, and that would be for a classification tree. So let's first talk about regression trees. And so basically, regression trees and classification trees work very, very similarly, except at the end, the prediction that you're making is numeric. And the way we decide where or how we're going to create these partitions is that the tree considers all of the possible partitions of the data. Okay, so it says, if you have 100 observations, it's going to try, creating a split where one branch, basically you line up all of the values and you try splitting it, so you have 1 versus 99, 2 versus 98, 3 versus 97, so on and so forth. You consider every single possible split, and the decision tree will evaluate every single possible split. The way it evaluates it, it looks at the residual sum of squares of the data after making the split, and whichever split is going to minimize the resulting residual sum of squares, that's the split that it's going to choose. So here's an example of a decision tree that was published in the New York Times back in 2008, so many years ago. But the reason why I mention this is because decision trees are very simple to explain and very simple for the public to understand. A lot of these other machine learning methods that we might cover or introduce, it's difficult for the public to grasp or understand. Even linear regression, as simple as we understand it, is actually a little bit can be a little bit tough in terms of fully understanding the slope. The public can generally understand that here's a line, and that's like your trend line. That part is simple, but getting much more beyond that can be a little bit tough. A decision tree, however, just using a decision tree to make predictions, is very simple and easy to explain. And so this was back in 2008. The political landscape was very, very different back then, and this was before the general presidential election. So this was during the Democratic primary. The two front runners for the Democratic presidential nominee were Obama and Clinton, and this decision tree was published. I don't know, maybe about halfway through the kind of that primary process. So just to, I guess, back up and give it some context, there's, you have the Democratic Party and the Republican Party, and each party kind of has kind of this primary nomination process to decide who is going to be their final candidate. And so during that time in 2008, both Hillary Clinton and Barack Obama were competing to become the nominee for president, and so they had looked at data from all of the states that had voted in the primaries up to that point, and then they were trying to use that to try to make predictions about how the remaining states were going to vote. And so they looked at all of the different counties that had voted up to that time, and looking at that kind of analysis, they created a decision tree, and this got published in the New York Times. And so, one of the first questions was, is the population of the county, is the county more than 20% black? And if the answer was yes, most of those counties, out of, I guess there would be 453 counties that fit that qualification of being more than 20% black. Of those, 383 voted for Obama, and so all the prediction would be those counties would go for Obama. And then the next question would be, is the high school graduation rate higher than 78%? If the answer to that was no, this would be counted as a county with less educated voters, so less than 78% have a high school graduation rate. Clinton won most of those counties. If you looked at high school graduation rate was higher than 87%, so after you go yes, then there's a further split. If it was higher than 87%, then it went Obama would win those 185 to 36, and so on and so forth. And you can kind of follow the path and make predictions based on how that county might vote as far as predictions go. Okay. To kind of illustrate how the regression predictions are made, we'll take a look at a very simple toy example where I have a total of 5 observations, okay? And so we are going to use the x variable to predict the y variable. X, I have 1, 2, 3, 4, 5, and then the actual values of y are 1, 1, 3, 7, and 8, okay? And again, it would be kind of silly to fit a regression tree to such a small data set, but I think it will illustrate how the calculations are made as far as where splits should be made. So first, we need to set a baseline, and the baseline is found by not having any kind of partition, or I guess all of the data belongs to just kind of one partition. And in this case, what is the value that you would predict for everybody? Okay, the value that you would predict for everybody is going to be the mean of the y values. So we have 1, 1, 3, 7, and 8. That adds up to 20. Okay, 20 divided by 5 gives me a mean of 4. And so our prediction for all of our observations would just be 4. And then we would calculate what is the residual and what is the squared residual. It looks like these are the absolute values of the residuals. I left out the negative signs. But so here, the actual value is 1. Our prediction is the mean 4. We have a residual of 3 or negative 3. And then when we square it, our squared residual is 9. Okay, same thing for the next observation, which is 1. We get a squared residual of 9. Here, the actual value is 3. We predict 4. That's a residual of 1. 1 squared is 1. The actual value is 7. We predict 4. Our residual is 3. 3 squared is 9. The actual value is 8. Our prediction is 4. That's a residual of 4. 4 squared is 16. And so when you add up all of these numbers, 9, 9, 1, 9, and 16, this adds up to 44. And so this forms our baseline. The total residual sum of squares with no partition is 44. And as far as a single prediction goes, the mean is going to minimize the residual sum of squares. You know, as far as making one value to predict all of these things, the mean is going to give you the minimum RSS. It minimizes the sum of squared residuals if you're going to just use one single value. Okay, and so our RSS right now is 44. This forms our baseline. Anything that we do further here, we're going to compare to 44 and see how much have we improved. So this is our illustration, and so here the actual values are 1, 1, 3, 7, and 8, and here we're predicting 4. These are our residuals of 3, 3, 1, 3, and 4, and when we square those, we get 9, 9, 1, 9, and 16 for a total of 44 in our residual sum of squares. Okay, and so now we are going to consider all of the possible partitions. We're going to consider all of the possible partitions. And so our very first partition that we will consider, so we use the x variable to make our partition, and so we will consider a partition between x is 1 and x is 2. So we'll make a split at, say, x is 1.5, okay, between our first two values. So I guess an implicit step here is we order all of our observations by x. So we have the smallest x up top, the largest x at the bottom, 1, 2, 3, 4, 5. And so if I make a split at 1.5, okay, I have partition A and I have partition B. So for partition A, I only have one observation, and it is y is 1. And therefore, my prediction for y hat, will just be 1. There I have no residual, and my squared residual is going to be 0. For partition B, I have the observations where x is 2, 3, 4, and 5. X is greater than 1.5. The y values are 1, 3, 7, and 8. If you add up 1, 3, 7, and 8, you get 19. 19 divided by 4 gives me 4.75. Okay, so that is going to be my predicted value for the remaining observations. So I plug in 4.75 and I measure my residuals. So 1 minus 4.75 gives me 3.75. When I square that, I get 14.0625. 3 minus 4.75 is negative 1.75. When I square that, I get 3.0625. 7 minus 4.75 is 2.25. When I square that, I get 5.0625. 8 minus 4.75 is 3.25. And when I square that, I get 10.5625. So here are all of my squared residuals. If I add all of them up, my total residual sum of squares is 32.75, which is a slight improvement over the original RSS of 44, but we can probably do even better. But the next slide will illustrate what this looks like. So here we have created a split at 1.5. For the values below 1.5, I'm predicting 1, so I have no residual here. For the values greater than 1.5, I use the mean, and here are the residuals there. And when I square all of them, the RSS is 32.75. Okay, let's consider another split. We're going to try splitting between 2 and 3. So we will draw our partition at 2.5, values less than 2.5. I have x as 1 and 2. My y values are 1 and 1, and so therefore I'm going to predict 1 for all of these things. I have a residual of 0, squared residual of 0, and 0 for observations in partition A. For the values greater than 2.5, my y values are 3, 7, and 8. 3, 7, and 8 add up to 18. 18 divided by 3 is 6. Therefore, my predicted value is going to be 6. So my residual, 3 minus 6 is 3. 3 squared is 9. 7 minus 6 is 1. 1 squared is 1. 8 minus 6 is 2. 2 squared is 4. So now my squared residuals are 0, 0, 9, 1, and 4, which adds up to 14. So that is going to be the total RSS for this split. And so here's our illustration here. The line goes perfectly through these two things. We have no residuals here. Over here, I predict a value of 6 for anything when x is greater than 2.5. Get a residual of 3, 1, and 2. When I square those, we get a RSS, residual sum of squares, of 14. Okay, I'm going to consider the next split, which will happen between x's 3 and 4. All right, so for values where x is less than 3.5, okay, I have these three values, x is 1, 2, or 3. The y values are 1, 1, and 3. That adds up to 5. 5 divided by 3 gives me 1.667. So my predicted value for these three observations is going to be 1.667. When I take the residuals, I guess I decided to include the negative sign over here. I get 0.667. I square that, I get 0.444. Here I get negative 0.667 again. 0.444 is the squared value. Here I get a residual of 1.333, and when I square that, I get 1.778. For values greater, where x is greater than 3.5, my y values are 7 and 8. The mean of 7 and 8 is 7.5, and so that will be my predicted value. So here, my residual is 7 minus 7.5. I get a residual of negative 0.5. I square that, I get 0.25. My residual here, 8 minus 7.5 is 0.5. I square that, and I get 0.25. And so here are all of my squared residuals, and when I sum all of these together, I get a sum of 3.1667. So this will be the total RSS for this particular partition. And so here, this is the illustration here. We have residuals of 0.67 and 1.33. We square all of those. Residuals of 0.5, and we square those and we get 0.25. And so our sum of squared residuals is 3.1667. Okay, we still keep going. We have one more partition to consider, and that will be a partition between 4 and 5. And so if I take all of the observations where x is less than 4.5, I get y values of 1, 1, 3, and 7. That adds up to 12. 12 divided by 4 gives me 3. And so therefore, my residuals are negative 2, which gives me a squared residual of 4. Negative 2, squared residual of 4. At 3, I have no residual, so squared residual of 0. And if my actual observation is 7 and I'm predicting 3, my residual is 4. 4 squared gives me 16. Meanwhile, as far as the value is greater, where x is greater than 4.5, I only have one observation, which is y is 8. Therefore, my predicted value is going to be 8. And we'll plug in a difference. We get a residual of 0. 0 squared is 0. And so when I add all of these up, my total RSS, 4 plus 4 plus 0 plus 16 plus 0, gives me an RSS of 24. And so you can see this is how it looks. And we can see, oh yeah, this is quite a big residual. And these are kind of big too. So the total RSS of that split is 24. So we have 4 partitions to consider between 1 and 2, between 2 and 3, 3 and 4, and 4 and 5, or 1.5, 2.5, 3.5, and 4.5. And so kind of reviewing all of these things, we had an RSS of 24, RSS of 3.1667, RSS of 14, and an RSS of 32.75. We would say the one that resulted in the greatest reduction in RSS is the one where we split between x is 3 and x is 4. When x is 3.5, if we create our split there, that is going to result in the greatest reduction of RSS. We went from an RSS of 44 down to an RSS of 3.1667. Okay? So, so that is how we would go about forming the partition here. And so I want to illustrate how this looks in R if we plug in our toy example in R. So, so here there's different libraries that you can use, and so the textbook ISLR uses the package tree. I will use our notes. In our notes, I will use the package rpart, and they end up making like the same decisions, and I will also show you how to do it in tidy models. But if you wanted to use rpart directly, the function says, hey, I want to create rpart r for I guess recursive partitioning. Our formula is going to be y tilde x, y as explained by x. We give it the data frame that holds our data. And then control is going to give like options on how to create a tree. And we have to use this because the default control options for creating a regression tree is that the minimum number of observations to even consider a split is going to be 20 observations. And again, we're dealing with this toy example where I only have 5 observations. It'd be kind of silly to do this in real life, but so we're going to change our the arguments so that it will still consider making a split even though we only have 5 observations there. Okay. And you could, if you wanted to, you could read more about rpart control and the documentation for that. So here I create my data frame. I have x as the values 1, 2, 3, 4, 5. I have my y values are 1, 1, 3, 7, and 8. And we're going to create a tree by saying use rpart, where y is explained by x. The data comes from the data frame df. And in the control arguments, I put in the argument that the minimum number, min split 5, saying like still consider making a split when you only have 5 observations. And this is the result. This is the resulting tree. And let me talk about how to read the results here, okay? And I think I've got it detailed out on this slide, but I will go ahead and just explain here. So here it says root 5, 44, 4.0, okay? And the key for reading it says node. This is node 1, okay? Or the and node 1, it denotes the split. Now this is the root of the tree, so there's no split yet, okay? And here we're saying how many observations are there? There's 5 observations. The y value is, if you have just these 5 observations, what is the predicted value for those 5 observations? That is 4. And so let me go back a few slides. So this was if we had no split whatsoever, okay, our predicted value was 4. Our predicted value for all 5 observations was 4. And then the RSS, when you used 4 for your prediction, your RSS was 44. Remember, we calculated the residuals, and we got 9, 9, 1, 9, and 16. When you sum those up, you got 44. And so that shows up on the very first line of our thing. It says if you didn't do a split, just left it at the root, you have 5 observations. Your total residual sum of squares, your deviance there is 44. Your predicted value there is 4. Okay, and then it says, okay, well, if you do the split, okay, your split could be at x is less than 3.5 and x is greater than 3.5. Okay, and so this corresponds. Remember, the winning partition that we chose was here, right, where we have x is less than 3.5 and or x greater than 3.5. We created a split here. And so what we see is we have 3 observations less than 3.5. Those 3 observations less than 3.5, what was our predicted value? Our predicted value is 1.667, and our RSS was 0.44, 0.44, and 1.778. And so, so that shows up right here. For x less than 3.5, That's our split. N, we have 3 observations. Our predicted value is 1.667 over here, our y value. And then the deviance, if you add up 0.44, 0.44, and what was it, 1.778, when you add all of that up, you're going to get 2.667, okay? And then for x greater than 3.5, that was the other part of the split, we had 2 observations. Our prediction there was 7.5 for those 2 observations, and the total sum of squared residuals there was 0.5. Okay, so going back to our split here, we had 2 observations greater than 3, where x was greater than 3.5. Our prediction was 7.5 for those 2 observations, and our squared residual were 0.25 and 0.25. When we add up, we get 0.5. So the total sum of squared residuals after the split was 3.1667, and so we can see, if I do 2.667 and 0.5, I would get 3.1667 as well. Okay, so this result basically summarizes the exact same things that we found when we did our tree right here. Okay, it tells us, what is the predicted value, where's the split? The split's happening between 3 and 4 at x is 3.5. What is your predicted value for y hat? When it's less than 3.5, it's 1.667. What's your predicted value for when x is greater than 3.5? It's 7.5. And then if you add up your residuals, squared residuals, what do you get? That's in the deviance column. So that is the resulting decision tree. This is how you read that, okay? And that's all detailed out on this slide. But yeah, that's what you get, okay? You can also call a summary on the resulting tree, and you'll get this, and it talks about kind of the complexity parameter regarding you have your first node, 5 observations, and what's the complexity parameter, the mean there. At node 2 you have 3 observations, and what's your mean? Your mean squared error is, so here we have the total sum of squared residuals was 2.667. If you divide that by 3, you get your mean squared error of 0.888. And then over here, node number 3, 2 observations, mean is 7.5. That your predicted value, and your mean squared error would be 0.25. Okay. And then the other part is the improvement here of 0.928, kind of corresponding to our complexity parameter. This is our improvement, and that is to say that our baseline residual sum of squares was 44. After we did the split, our residual sum of squares went down to 3.1667. Okay, so we went from 44 down to 3.1667. So that is a reduction of 40.833. Okay, almost a reduction of 41. So 40.833. 40.833 divided by 44 gives us 92.8%. Okay, that is the proportion that we've reduced, and so that is our improvement number. We went from 44 down to 3.1667, so our improvement rating is 92.8%, 0.928, and that is that's given in the summary there. If you wanted to do something similar with tidy models, we can definitely do that as well. So here I've loaded up the tidyverse and tidy models, and we're going to say I want to create a decision tree. Okay, I want to create a decision tree. This is the kind of the parsnip specification. As far as the engine I'm going to use, I'm going to do an rpart for my engine. The mode is I'm going to do a regression tree. And then the argument, as far as, hey, still consider making a split even though I only have 5 observations, that goes into my argument for a decision tree. And so here I'm going to say, go ahead and take that tree model and fit it to our data. And our formula is y tilde x. And we say, hey, go ahead and fit that thing. And so here is the resulting fitted tree underscore fit. And we see we get, the exact same kind of output regarding the rpart. Okay, because basically tidy models translated our request into instructions that rpart understands, and rpart does its job, and it creates the same resulting tree. Okay, So, split at 3.5. So same exact output that we had before. Okay. So that's the example for our toy data set, and the concept applies with a larger data set. Okay, so it was very simple. We only had one x variable, and we had 5 distinct values. So therefore, there were 4 splits to consider, right, between 1 and 2, 2 and 3, 3 and 4, 4 and 5. Okay, let's say we had a second x variable. Okay, then we would consider all of the possible splits using that one. So we would have a total of 8 splits, right? So we'd split between 1 and 2, 2 and 3, 3 and 4, 4 and 5 on x1, and then we would look at variable x2. We would sort those in order from least to greatest, and we would consider splitting between the first and second, 2 and 3, 3 and 4, 4 and 5 on x2. Okay, and we would consider all of the splits on variable x1, and we would also consider all of the splits on variable x2. So we'd have a total of 8 possible splits to consider, and then again we would just choose the split on the variable that resulted in the greatest reduction in RSS. Okay, if you have a bigger data set, let's say 100 observations and 5 variables, okay, you would have a total of 495 partitions to consider. Okay, and assuming all 100 observations had unique x values. Okay, so you would say, all right, let's look at variable x1. There's 99 possible partitions to consider. Let's look at variable x2, 99 partitions to consider, so on and so forth. You do this for all 5 variables, and again, of the 495 partitions to consider, you are going to use whichever split results in the greatest reduction in RSS. Okay, and then once you split the data, then you repeat the process recursively. Okay, so after you split the data, let's say you have 100 observations. Let's say your first split, okay, you use variable x1 and you split when x is, I don't know, greater than 7 or less, 7.5 or less than 7.5. And let's say you end up with a split where you have 35 observations on one side of the split and 65 observations on the other side of the split. Okay, well, then you go down you kind of that first branch, and you say, okay, now I'm going to treat as if my entire data set is just these 35 observations. Okay, and we're going to look at my 5 variables. I have 35 observations, so therefore I have 34 possible splits to consider for each of the 5 variables. So what is that? 34 times 5, that's 170 possible splits to consider. I look at all 170 splits, and I pick the one that's going to reduce the RSS there. Okay, and then so maybe it splits it 15 and 20. Okay, then I look at those 15 observations and I consider all possible splits. And then once you kind of, and maybe our stopping criterion is we need to have a minimum of 10 observations to continue. So maybe I look at the 15 and I split it, and I get a split of 7 and 8, and then I say, okay, well, both of these things are less than 10, so therefore I've stopped splitting. Okay, so then I kind of go back up the tree. So prior to that, I think we had 35 observations. We split it from 15 and 20. So then I look at that group of 20, and then I do a split. Maybe I get a split of 8 and 12. I leave the 8 alone because that's less than 10. I go to the split with the group with the 12, and maybe I split that, and I get 6 and 6 or whatever. It doesn't matter. Okay, and then so I've reached the stopping criterion for everything on that group of 35. Then I go over all the way to the other side. I've got 65 observations, and then I just kind of recursively split until I reach some kind of stopping criterion. So a common choice for stopping criterion is minimum number of observations in each resulting bucket. So we say, hey, if you end up with 10 or fewer in kind of your terminal node, that's a good time to stop. Or you might have a maximum tree depth, saying like, okay, if this is the result of after 4 splits, then just go ahead and stop. Okay, and then whatever you have in that final node, okay, with those observations, you predict a single y y value, just generally the mean of that bucket, and you're going to predict that value for all of the observations that kind of fit in that classification or in that bucket. Okay. If you do this, your resulting tree often overfits the data, creates maybe a few unnecessary partitions, and so we might want to go back and prune the tree. Okay, so we have a few ways to kind of control for this, but let's just revisit our original data, okay, our toy example, and we'll put in some bad control options. Okay, so here we'll say, hey, consider a split even though you only have 2 observations. Okay, and so here I'm using tidy models, and we're going to say, hey, consider making a split even though you have only 2 observations, even if you have a cost complexity of 0.01. This is kind of like your minimum cost complexity parameter to reach. And then so we'll go ahead and make our bad tree. This way we'll take our bad tree model, fit it to our data, and basically we have created a partition for every unique value of y, basically. Okay, so our first split happened between x is less than 3.5 or x is greater than 3.5. If you go down the path where x is less than 3.5, then you see another split where x is less than 2.5 or x is greater than 2.5. Okay? If x is less than 2.5, we have 2 observations, we predict a value of 1, and you have no deviance there because it predicts it perfectly. When x is greater than 2.5, you predict a value of 3, and you have no deviance. If you went down the other path where x is greater than 3.5, you would consider another split where x is less than 4.5 or x is greater than 4.5. And again, these values all predict the values perfectly. You get no deviance in any of this. Okay, so we produce 4 terminal nodes, which is equivalent to the number of unique y values that we have in our data, and that's we're overfitting our data. And so to kind of avoid this problem of overfitting, we can do what we call pruning the tree. So we're leaning hard into this tree metaphor or analogy. And we're going to remove, I guess, the weakest link, or kind of the most unnecessary branch, kind of one at a time until we achieve some kind of desired complexity. All right. So when we go back to this tree, we might consider removing the split at 2.5, or we might consider removing the split at 4.5. Okay. So if the way we are going to decide is we're going to look at how much improvement in RSS do we get by including that particular split. Okay. So what we can see is that the split at 2.5, prior to that, we had a total deviance of 2.66. After the split at 2.5, we go down to a deviance, of 0. Okay, so we've reduced our RSS by 2.66. Here, the split at 4.5. Prior to that, our total deviance was 0.5. After the split, we have a total deviance of 0. Okay, so we've reduced our deviance by 0.5. Okay. So that's listed off here. If you do that as kind of a fraction of how much RSS did we reduce, okay, the split at 2.5, we went from 2.66 down to 0. So that's a reduction of 2.66. 2.66 divided by 44 is around 6%. So that's the measure of its improvement, and that's known as our complexity parameter for that split. The split at 4.5, again, prior to that split, our total deviance was 0.5 for this node. After the split, our total deviance is down to 0. And so therefore, the reduction in RSS is 0.5. Okay, 0.5 divided by 44 gives me 0.0114. Okay, and this is the complexity parameter of this particular split. Okay, which shows up if you ask summary. All right, so we'll take our tree fit, and we say, hey, give me the summary on this R part thing, and it says, our first kind of node, this primary split was x less than 3.5. That improved our RSS by 92.8%. So that's our complexity parameter. Okay, and then we have the split at 2.5. That improved our RSS by 0.06. Okay, I mean not our RSS by 0.06. Our improved it by 2.667, which corresponds to improvement of 6%, and that's our complexity parameter. And then finally, here we had a split at 4.5, and again that reduced our RSS by 0.5, so we get a complexity parameter of around 1%. Okay, and so that would be kind of our weakest link. And so if we do a prune, this would be the split that gets pruned. Okay. So in the summary, we can see, that the complexity parameter of node 3 is 0.01. Complexity parameter of node number 2, this one right here, is 0.06. So what I can do is, when I specify my tree, I can specify cost complexity of, say, 2%, something greater than 1%, but less than 6%. And this will create a tree that basically won't produce a split that has a cost complexity less than 2%. So here, this is the resulting tree. Creates a split at 2.5, but it does not create the split at 4.5. Okay. And then again, if I wanted to prune it further, I can increase my cost complexity and to say 10%. So that's a number greater than 6%. And we'll say, hey, you know what? Only consider making a tree if the improvement in RSS is greater than 10%. And so if you do that, then we only have the split at 3.5. Okay. And so this will be kind of a simple tree, probably doesn't overfit the data, but again, this is just a toy data set with only 5 observations, so probably not a very good data set even to start with. Okay, so let's just try a slightly more complicated example data set. And so one of the data sets included in R, I think, is this 1990 consumer reports data. Okay, it's they looked at a bunch of cars from 1990, and we're going to try to predict the price of the vehicle based on a few factors. One is the country of manufacture. One is the type of car, whether it's like a sedan or a truck or a sports car or something like that. And then the mileage, I think, is how fuel efficient the vehicle is. Okay, and so here I'm going to just give it with the default kind of decision tree arguments. Again, you can customize some of these things. We're going to set the engine to be R part, mode to be regression, and here we're going to say we're going to fit this. This is going to be the formula that I use. Okay. All right, and so this is the resulting tree. A little bit more. We have a total of 117 observations in total. Our deviance is huge because we're looking at like price numbers, which is in the thousands. Okay, and so if you just take the average of all 117, your predicted value for the price of the vehicle is $15,743. So again, this is 1990, so I don't know, that's like what, 34 years ago or something. This is the thing. All right. So our first split is a categorical split. Either we have a large or medium-sized car, or we have compact, small, sporty, or van. If it's a compact, small, sporty, or van, there's 80 observations. Our predicted value is 13,035. If it's a large or medium vehicle, there's 37 observations, and our predicted value is 21,599. So we can see the large and medium vehicles cost more. The compact, small, sporty, or van vehicles cost less. This is the total deviance, and we can see, okay, well, if I need to pull up like a calculator here. Let me pull up a calculator to try to estimate how much improvement we got. Okay, so our total deviance afterwards is what? 3322389000 plus 222935100. Okay, so that adds up to 555174000. Okay, let me subtract off the original 740747300. Okay, so this is how much we've reduced. That's how much we've reduced our RSS by. So what is that? What proportion is that? We're going to divide by 740747300. So that's a reduction. So by including this split, we reduced our total RSS by 25%. 25%. Okay. So so that's the first node. We say, hey, what type of vehicle, large or medium? Okay. Let's look at these 80 observations. We do a further split. We say, and then according to this, considered all of the possible splits, and it says, okay, if the vehicle was manufactured in Brazil, France, Japan, USA, Korea, Mexico, or USA, we have 69 observations, and our predicted value is 11,555, and this is kind of your RSS there. Or if it is a vehicle that came from Germany or Sweden, so a compact, small, sporty, or van vehicle that came from Germany or Sweden, then our predicted value is 22,317. So I guess the German and Swedish vehicles, so what's that? BMW, Mercedes-Benz, Audi for German vehicles. Sweden, I think, is Volvo and Saab. Okay, so nice vehicles. There's only 11 observations, but it's enough, to kind of reduce our RSS there. So this is what we get. Over here with the large and I guess after that, no further splits. But then for these 69 observations, we can do a further split, either small vehicles or compact, sporty, or van. Small vehicles, we predict $7,629. These, we get that. And then if you do that, further splits there. Okay. Same kind of thing, just kind of further partitioning each of these things. Okay. If we look at the resulting summary, this will give us a measure of our complexity parameters and, kind of the different splits. And so we can see that initial split, remember, we had a reduction in our RSS of around 25%. And we can see that is indeed the corresponding complexity parameter for that particular split. So that first node, we had 117 observations. And if we said, if we went down this side, okay, either compact, small, sporty, or van, there are 80 observations. If it's large or medium, there's 37 observations. And we could see, okay, some of these splits, and these are the different results that we end up getting, okay? So regarding the complexity parameter there, your mean ends up as that, okay? So this is just kind of the summary on the on all of these different splits that we got, okay? So you might wonder, like, okay, well, how deep should the tree go? What kind of splits should I consider? All right. So this first split, sure, I'll do that. But some of these later splits, okay, like the node here, only improves the RSS by a little over 1%. Okay, so some of these splits later on, improve our RSS, but only by a little bit. Okay, so for example, I think this split right here, prior to the split we had, I don't know, whatever this is, and after the split we have something less, but that improvement is only a little more than 1%. So you might wonder, like, okay, is it worth still having that split or not? And we can try to choose, how much of a complexity parameter, how much improvement do we actually want before we stop the tree? Okay, and so we can say we can create a tuning grid to decide how much, like, what our minimum complexity parameter should be. Okay, so we'll use cross-validation, and we'll use tidy models, and we'll use the tuning grid to try out, okay, what's going to happen if you fit a tree where you have a minimum of, say, 1% for your cost complexity, and you include all of these splits. What's going to happen if you set up a tree where you say your minimum cost complexity has to be 4%, okay? And in that case, you wouldn't consider the splits 5 and 6, and you'd stop your tree after, split 4, okay? So how's that going to go? Okay, so we want a range from around, say, 0.01 to 0.25. Now, cost complexity, that parameter, okay, generally uses a log 10 transformation. So we're going to do something around, say, -2 to -0.5. -2 would go to be 1%, and our upper range of -0.5 is around 30%, 32%-ish, okay? You can also do different parameters to kind of mess around with regarding decision trees, and you can read more about that here. But here we'll do cost complexity, but the tree depth, how many how many splits to consider before you stop the tree and things like that. Okay, so for here we will set up our decision tree. Okay, this is our tunable tree model. We're going to create a decision tree, and our cost complexity, rather than just specifying a number, we're going to make it a tunable parameter. We'll keep our engine at RPART and mode regression. Now we want to set up a cost tuning grid, okay? And so we'll use grid regular, and we want to tune the cost complexity parameter, and so we will consider a range going from basically -2 to -0.5, do a log 10 transformation, and I'll consider 10 possible cost complexities. So we'll go anywhere from 1% up to 30.316 for a cost complexity. And so this is spaced out in a log form versus without the log transformation, it will be linear, and it would be like spaced out. The difference between each of these spaces would be linear, versus here smaller spaces when they're smaller, and then bigger spaces when they're bigger. So here we're going from 1% to 0.0147 to 0.0215, and we're scaling up to from 0.1 to 0.147 to 0.215, and so on and so forth. So we have this. We're going to consider different kind of cost complexity values here. And so here, to use tidy models to try out all of the different cost complexity values, we're going to use V-fold cross-validation. So we set that up. We take all of our data, okay? So we take our consumer reports data, which had 117 observations in total, and we're going to do V-fold cross-validation, and that sets up our fold. I think default it's 10 folds here. And so now we're going to set up our workflow and fit it using tuned grid. Okay, so our workflow is just take our tunable tree model, and then we don't have a recipe, we just take the formula. And this is the formula: is predict the price based on mileage, type, and country. And then now we're going to take that tree workflow and throw it into the argument tune grid. Okay, so this is kind of like fit, It's like take your model and fit it to the data, but here we're going to fit using cross-validation and try out all of our different cost complexity parameters. And so so this is just a real efficient and a nice way to, because you could do this manually, right? You could say, hey, I want to set up my, like back here, when you set up your tree model and do tree fit, you could decide to try out a model where the cost complexity parameter is 1% and then 1.47% and so on and so forth. But this will just do it all in one step here. We just say tune grid. The resamples is your folded, your vfold cross-validation data after you've done the folds, okay, after you set up the folds using vfold cross-validation. And then the grid is the tree grid that we set up back here, okay? And then Tidy Models runs through all of this, and it's going to store everything in the tree results. And so using the tree results, I'm going to ask to collect the metrics, okay? And then let's look at the RMSE values, okay? And then we'll arrange it based on the mean RMSE. So this is what we get. When our cost complexity is around 3%, our average RMSE is 5892. And so these are the different values that we get. And so we can see, once you have a really high cost complexity, so this is, remember, bias variance trade-off, high cost complexity parameter indicates high bias, low variance, okay? And so we're getting not super great. But if we have too low of a cost complexity, we're overfitting our data, okay? And so 1% or 0.0147, our performance isn't as great. And so it seems like we get our best performance around 3 to 4% for our cost complexity parameter, okay? Although the difference here, not huge, but it does seem, this seems to be the kind of the sweet spot as far as our best performance, okay? So knowing the vfold cross-validation results, we know that it is subject to randomness, so we could try it again. So here, using our particular cross-validation, we got around 3 to 4% as our best cost complexity parameters. Let's try this again. Here I'm going to try a different seed and set up different cross-validation. So I'm going to run through the same process again, okay? But this time just doing a different seed. So I did 10-fold cross-validation, but now I'm going to change the seed. So I'm going to get like a rearrangement of 10-fold cross-validation. We'll use the same kind of workflow again, our tunable tree model, and then we're going to fit it to, using the same kind of tuning grid to figure out what's the best cost complexity there. All right, so here I run it again, and I get slightly different results. So here my best performing cost complexity was 2%, and 3% is second best, and 4.64 is third best, okay? But if you look at the average RMSE here, the difference between 2%, 3%, and 4%, very, very little, okay? They have almost all the same values here, so 5603, okay? So let me just go back a few slides to kind of the first time we ran cross-validation, okay? We got our best performance at 3% and 4%, and our RMSE was different there, but these were kind of our two best things. And our 2% model, for whatever reason, didn't perform super great, but this is what we got, okay? So trying out different folds of our data, we we get slightly different results. So what this seems to suggest, okay, these results over here and these results over here, looking at all of these things, the difference between kind of the first 5 and the remaining 5 seems to show like going from, again, our first 5 to the remaining 5, there's kind of a bigger jump in kind of the RMSE from, I would say, between 5 and 6 versus everything else, okay? So 2%, 3%, 4% seems to be the best, and maybe which one's the best depends on your cross-validation results. But this gives us an idea of how we should, what cost complexity parameter we should go with, okay? So it's not an exact thing. Again, we're not using mathematics in terms of like some analytic approach, but we're just kind of like trying it out, seeing how it performs. And we know that cross-validation is subject to randomness, so we try it a couple times, and we're hoping our results align. And here they kind of align in that they're both agreeing that 3%, 4% probably seems to be a good number, and they all seem to agree that 14, 20, 30%, these are all bad numbers to use. Okay. Here's another seed. Over here, we got 2%, 3%, 4% as kind of our best performing ones. So that seems to be kind of the general consensus. 2, 3, 4% seems to be performing well, okay, regarding the cost complexity there. Okay, so that is just for a decision tree. And we can use the decision tree as kind of a foundation to build up bigger models, okay, more useful prediction models like random forest, okay? So so decision trees are great, but overall, the prediction performance of a single decision tree is not going to be very good. Remember, at the end of your decision tree, you might have 8 observations in a single leaf or single node, and all 8 of those observations get the exact same predicted value, okay? The nice side of a decision tree is that it's very easy for a human to understand, all right? You can just kind of follow the thing, and it's very easy to say, okay, if the x is this, then you go down that path. If the x is that, you go down the other path. But again, predictive performance of the tree, not very good. So we have a few methods to kind of improve tree performance, okay? One of the methods is bagging, okay? Bagging is the application of bootstrap to a decision tree. So bootstrap is the idea of resampling your data with replacement to get a slightly different version of your data, okay? It seems a little bit silly, but it's basically you're assuming your data is representative of the population, and you're going to say, hey, what if I just resample it, resample my data to get like as if I'm drawing another random sample from the population, okay? And so when you do this, you're going to get a slight variation of your data, and then you fit a decision tree to that slight variation of your data. You fit a decision tree to your bootstrapped sample. Okay, and so therefore your decision tree is going to be, each of these decision trees created based on the different bootstrap samples will be slightly different. And then after you set up all of these trees, you take your test observation, you run it through all of the different decision trees that you've created, and you average their predicted values, okay? Or if you're doing classification, you use a majority vote. So anyway, let me just show you what we're going to do, okay? So here I'm going to just take our toy data, and again, it's silly to do this with the toy data set, but this I think will be illustrative. So here I start off with my original data, okay? But here I'm going to do a resample, okay? So I had 5 observations in my original data, and I'm going to draw 5 observations with replacement, okay? So I have my 5 original observations. I draw them with replacement. So I draw an observation and I put it back in, and so what happens is sometimes I draw the same observation more than once, and I won't draw any some observations at all. And so when I resampled my data, I ended up drawing the 4th observation twice, okay? And I never drew observation 1, okay? So this is now my resampled data, and I say, okay, if this is my data, what should my tree look like? So I fit a decision tree, and when I fit the decision tree, it says make a split where x is 3.5, okay? And when x is less than 3.5, the prediction you're going to make is going to be y should be 2. And when x is greater than 3.5, the prediction you should make is going to be 7.33. So that is our first tree. Our first tree says make a split at 3.5, but your predicted values are going to be 2 and 7.33. I take my original data, the 5 observations, and I sample it again with replacement. This time I selected row 3 twice, and I did not select row 2 at all. So my observations are this. And I say, all right, where should I make my split this time? So here, the split, again, I think ends up at 3.5, okay? But my predicted values are slightly different. When x is less than 3.5, we're going to predict 2.33. And when x is greater than 3.5, we're going to predict 7.5. And then I run this one more time. And I say, resample your data. And just kind of by coincidence, I ended up selecting observation 1 3 times. And I ended up selecting observation 4 twice. Okay? So now it says, where should I make my split? Well, I'm going to split between x's 1 and 4, so the average of 1 and 4 is 2.5. So we're going to split at x is 2.5. When x is less than 2.5, we're going to predict y is 1. And when x is greater than 2.5, we predict y is 7. So that's just kind of by coincidence, this is what we get. Okay, so I have 3 decision trees. And let's say I have a test case. Let's say my test case is x equal to 4. I'm going to run this test case through all 3 decision trees, okay? So the first decision tree, if x is 4, okay, that falls down the side where x is greater than 3.5, we predict 7.33. For my second tree, when x is 4, that falls on the side x is greater than 3.5, and we predict 7.5. For our third decision tree, when x is 4, it falls on the side that x is greater than 2.5, and we predict 7. Okay? So tree 1 makes a prediction of 7.33, tree 2 makes a prediction of 7.5, tree 3 makes a prediction of 7. And what we do is we take the average of these 3 trees. The mean of these 3 trees is 7.278. And that's going to be my prediction when I do bagging. Okay? So that's how bagging works. You resample your data, and you get slight variations of your data. You fit a tree to that, data variation, and then you build up a whole bunch of trees like that, and then when you make a prediction, you run them through all of the trees, and then you average your predictions. So this is kind of how it works with a toy data set. Obviously, in real life, you would, make a whole bunch of these trees, and that yields what we call the kind of that's a step towards building the random forest. So bagging alone, however, is not a recommended strategy, because what ends up happening, even though you get variants of your data, your trees end up looking too similar to each other. Okay, your trees end up looking too similar to each other. One issue is that some of the variables, some of your predictor variables, could be like too strongly correlated with the response variable, and so almost all of the trees end up using the same kind of predictor variables, and even though your predictions will be slightly different, all of the trees end up looking really, really, really similar to each other. So the random forest purposely kind of makes each of these trees like each individual tree not to it impairs each individual tree. Okay, and so in a random forest, what happens is we randomly select a subset of the available variables. Okay, so we have a random selection of the variables that the tree is allowed to use, okay? So the individual trees are kind of impaired in that these trees can't use all of the available variables to create a split, right? And so I don't know. It's kind of like if you wanted to predict the cost of a house, it sure would be helpful to know the square footage of the house, okay? But we're going to say, hey, I want you to create a tree, a decision tree, but you're not allowed to know the square footage of the house. So you have to use other variables. And you say like, so maybe you're not allowed to use the square footage of the house or the number of bedrooms in the house. So now you're trying to figure out, okay, how can I figure out important, like how big the house is? So you might use another variable like how many bathrooms there are. Or you might have to use something else. And you might say like, okay, well, I'm going to look at, the quality of the kitchen. And we're going to hope that if the kitchen is really nice quality, then that's got to correspond to like an expensive house or something like that, right? But individually, like if you don't know the square footage of the house, that tree by itself probably not going to perform very well. But the hope is that by having a whole bunch of these suboptimal but highly diverse trees, the resulting prediction made by kind of the aggregate of all of these trees will be better, okay? Another silly analogy is, let's say you're putting together a team, like a superhero team, right? You're putting together the Avengers or something for some kind of mission, right? If, if everyone has sight, then very likely everybody depends heavily on using vision to navigate, okay? As sight is considered one of our most important senses, right? But if you include a person on the team who's blind, right, like Daredevil on your team, then you'll have somebody who doesn't need or depend on sight for navigation, but uses their other senses, okay? And so, if you end up in this kind of novel situation where, vision isn't that helpful, then, having Daredevil on your team, having a blind person who can kind of navigate and still kind of get around would be very helpful, okay? So it's kind of like, when you create a superhero team, you don't, like, Captain America is great, but you don't want 5 Captain Americas. You want to have, like, a mix of teammates so that, together, I don't know, whatever. They things are better that way, right? And that's kind of the idea of the random forest, is you don't let them all use the same kind of like, if everybody picks super strength, then you're not going to have great diversity on your in the forest. And so the forest purposely says, hey, you're not allowed to pick this variable. Okay, you're not allowed to pick this thing. You got to build your tree out using something else. Okay, so the random forest kind of works like this. You resample the data, much like bagging. Okay, but when fitting the tree, you choose a random subset of the predictor variables in the data set. You fit a whole bunch of trees. Each tree uses a different subset of predictor variables, and now when it's time to make a prediction, you take that your test case, you run it through all of the different trees available, and then you average all of their predictions, okay? And that's how it works. So here is, this is taken from Wikipedia. You have your instance and you run it through each of these different trees. This tree predicts, some number or a certain class. So here this is a classification tree. We have classification trees where tree 1 predicts class A and tree 2 predicts class B and tree N predicts class B, but works just as fine for regression trees. Tree 1 predicts 35 and tree 2 predicts 42 and tree N predicts 27, and then you take the average or you do majority voting there. Okay, so here we can do this with tidy models as well. We're going to take this data set called air quality, and we have these different variables. I don't know what they mean. Solar R, wind, temperature, month, day, different variables. And we're going to try to predict this value for ozone. So the ozone layer is important, but at surface level, ozone is actually not good for human health. All right, so so we want to kind of see like where what variables are related to ozone. And so to create a random forest in Tidy Models, we can set that up with parsnip, and the model specification is random_forest or rand_forest. There's a few different engines available. One is the random forest engine, but Ranger is a newer package, newer library that also fits random forests. I guess it's based off of the play on words of having a forest ranger, and its performance is just faster. It's much better. You get similar kind of predictive capabilities, but its computational speed much better. So I highly recommend the use of Ranger over, say, just random forest. And so so we'll go ahead and set this up. My workflow, I'm going to add the model RF model to it. And then as far as the formula, we're going to just predict ozone based on all of the other variables. Okay. And now we just run fit. Okay. And we'll say fit data to air quality. Now, when we do this, we get an error. It says missing data in the column solar.r, right? So if we look at this, we go, oh yeah, we do have some missing values. So that's one thing, is that a random forest isn't able to make predictions if you have missing values, right? Because it uses these branches, and it says, okay, if you go down this branch, then this is your prediction. If you go down that branch, this is your prediction. And if you're missing, we don't know which branch to send you down. So what we have to do is we have to fill in some values. And so what we're going to do is we're going to create a recipe. And so this is a simple recipe where we're going to fill in any of our missing values by using impute. So we're going to do step impute mean. And so that's going to go through and take any missing values in this variable solar.r, and it's going to calculate the mean of solar.r, and it's going to fill it in for anything that's missing. And so that's going to avoid the problem of having missing values. Now, is using the mean for everything the best solution? I don't know. You have different options. You can use like k-nearest neighbors and try to fill in missing values that way. There's different options, but a simple method is to fill in the missing values using the mean. So that's so we're going to create a recipe. So rather than just in our workflow, rather than having the model and formula, we'll have a model and a recipe. So it's our simple recipe by just kind of imputing the missing value. And then my workflow, we have the model and the recipe. We add the recipe and add the model. And now we'll try fitting our data. And again, we run into a problem now. This time, so errors are okay, and error messages are helpful, right? And as long as you're getting a different error message after you tried an attempt, that means your fix was at least successful in changing something. So earlier, our error message was we had missing data in the column solar.r, and now I have a different error message, missing data in the dependent variable. And again, I should have picked this up. We do indeed have a missing value in the variable ozone, which is what we're trying to predict. Okay, so we will go ahead and fix that up. Okay, and so now in my recipe, I'm going to just change my recipe. We will add another step where we're going to say, hey, if the ozone value is missing, just throw those observations out. Okay, we could have done that with solar.r, but we might have been throwing away some good observations. So, what you decide to do is what you decide to do. But in this case, we're going to impute missing values for solar.r. And as far as the ozone, we're going to just throw those observations out. Okay. If you are an expert and you know things about this, you might say, hey, you know what? When ozone's missing, we should impute the mean. Or if solar.r is missing, we should throw it out. And how you want to handle your missing values is entirely up to you. This is how I've decided to handle it. Again, I'm not a air quality expert. I don't really know what I'm doing, but these seem like reasonable steps. So that's what I've gone ahead and done. Okay. And so this is just to illustrate, these are some of the steps you can take as far as a recipe goes, as far as pre-processing your data. You don't have to manually go through and clean up the data yourself. You can use tidy models to take care of these pre-processing steps, like imputing the mean or throwing out missing values. Okay, and so now my workflow, I'm going to add that recipe, add the model. Now we're going to fit it to the data. Okay, and this got kind of printed pretty big, but this is the resulting fit. And it says, oh, you had the preprocessor where you imputed the mean and threw out the missing values, and this is the kind of the resulting call there. Okay, so here we can say, all right, let's go ahead and make predictions. Now again, here we didn't do any kind of train test split. We also didn't do any kind of cross-validation. And so again, in kind of a real life process, you'd probably want to do some cross-validation and whatnot. But here I just want to kind of show you, this is how we would go about making predictions. So I'm going to take my fitted model, RF-fit. We will make predictions on the original data set, okay? And we'll bind the predicted values to the actual response variable ozone. This is what we have. We still have the original things. We still have some missing values there, but that's okay. And we can measure kind of our RMSE. All right, and so this is what we have. Okay, so our RMSE 8.24, and that's going to be kind of some measure of performance there. And again, in the grand scheme of things, you'll fit a whole bunch of these different models, try out cross-validation to try to see how well your data will your different models will perform. Okay, one more thing, one more model I want to talk about is our boosted trees. Okay, and boosting. And so another popular machine learning model or algorithm is called XGBoost, which is a form of boosted trees. And so I want to talk about how boosted trees work. And it's different from random forests, but there are similarities because at the core we are using trees. Okay, so what boosting does is we select a learning rate. So a normal random forest is you kind of you have a whole bunch of trees, and you take your test case and you run that test case through each of these trees, and each tree predicts a value, and you take the average. What boosting does is you have a whole bunch of trees, okay, except each tree is what we call a stump, and there's only one split, okay? You don't have multiple branches to go down. You either go down the left or right, okay? And then when you fit a test case to the stump, you don't actually take that prediction directly. You just take the output of the of that tree, that stump, and you use that to just make a slight adjustment. Okay, you don't take the prediction at face value, but you apply a learning rate, and basically you just adjust it. All right, you see, you might have a learning rate of 1%, and you'll say, okay, so this, maybe the tree says predict 100 or something, and you just say, okay, well, rather than going up 100, I'm going to just do 1% of that, and I'm going to just notch my prediction up by 1. Okay, so with boosting, we start off by predicting the mean for everybody, okay, and we calculate all of the residuals, okay. So we calculate all of the residuals and we say, all right, so some things are positive and some things are negative. And then we fit that decision tree with the response. But then when that response says, increase it by 100 or decrease it by 50, rather than increasing by 100, we multiply it by our learning rate. And I say, just increase it by 1. Or rather than decreasing it by 50, we multiply it by your learning rate and we say, decrease it by 0.5. So we make these really tiny little adjustments with each of these things. And then after I make an adjustment, I try fitting another stump or boosted tree. And I keep doing this over and over and over again. And our final prediction is the sum of all of our different boosted trees. So we take, we fit a decision tree, which is this F hat B, okay? And rather than using that directly, we multiply it by our learning rate, like 1%, some tiny number. And so my prediction is updated by just a tiny bit. And then I say, okay, what are my new residuals now? And I just do this over and over and over again. We add all of the different boosted trees together, and that's going to be kind of my final prediction. We'll go through the toy example again, and I'll just kind of go through like 3 boosted trees here, okay? So another way to think about like kind of boosting and learning rates is that, we're making tiny, tiny little adjustments. So, it's like, again, adjusting the shower temperature in your shower, right? If it's too hot, rather than cranking it all the way to cold, you just make tiny, tiny little adjustments. After you make the adjustment, you check, is this the right temperature? If it's not, you make a tiny adjustment, okay, until it feels right. So, so here we fit small trees. We sometimes call them stumps. Low variance, high bias trees. So just 1 node, 2 branches, and then we train on the errors. After we make the prediction, we update our residuals. Okay. So for boosting, for this toy example, I'll use a lambda learning rate of like 30%. Normally the learning rate is like 1% or something really small. Okay. And here I'm going to just fit a couple trees, and normally in boosting you fit like thousands of these trees. Okay. But hopefully this will still illustrate what's happening. Okay, so here's my original data. X is 1, 2, 3, 4, 5. Y is 1, 1, 3, 7, and 8. And I say, all right, let's calculate our prediction. We predict 4, and all of my residuals now, I have -3, -3, -1, 3, and 4. And so we fit a tree to our residuals, and it says, hey, make your split at 3.5, okay? And if it's less than 3.5, your predicted value is -2.33. And if it's greater than 3.5, your predicted value is 3.5. Okay? Which makes sense because when we first fit our tree, our predicted value was 7 and then 1.667. Basically, we subtracted off 4 from all of our predictions because that's what we did. We subtracted 4 from Y to get our residuals. Okay, however, rather than saying, okay, I'm going to adjust it down by -2.33 or adjust it up by 3.5, I multiply it by my learning rate. My learning rate here is 30%, okay? Normally it's something like 1%, but here my learning rate is going to be like 30%, and so therefore my predicted value is going to be 4 plus 30% times -2.33, and that gives me 3.3. Okay, over here, my predicted value is going to be 4 plus 30% times 3.5, and my predicted value is 5.05. Okay, what are my residuals? My residuals now, if the actual value is 1 and I'm predicting 3.3, my residuals are -2.3, -2.3, -0.3, +1.95, and +2.95. Okay, so here I fit a boosted tree. My predictive performance is terrible, but that's kind of the point where we have individually each of these trees are terrible. But we're going to do this sequentially, okay? So now here are my residuals, -2.3, -2.3, -0.3, 1.95, 2.95. My x values are still 1, 2, 3, 4, 5. I'm going to fit a tree here. when I fit a tree here, it says, hey, this is your split. Your split should be at x is 3.5, and you're going to predict negative 1.63 or positive 2.45. Okay, this is how much I should make my adjustments, but we apply the learning rate. So, you know, my predictions used to be 3.3, and my prediction I'm going to adjust by negative 1.63, but I multiply that by my learning rate. So now my prediction is 3.3 plus 0.3 times negative 1.63. I get a prediction of 2.81. Doing that over here, I get a prediction of 5.785. These are still terrible predictions. My residuals are now negative 1.81, negative 1.81, 0.19, 1.215, 2.215. And so here, this is what we have, and I say, okay, here are my residuals. Let's fit a tree to these residuals. And when I fit a tree to these residuals, it says you should make a split at 2.5. At 2.5, if it's less than 2.5, you're going to predict negative 1.81. If it's greater than 2.5, we're going to predict 1.206. Okay. And again, we apply our learning rate here of 30%. And so now our predictions are 2.267, 3.172, 6.147. Okay, still terrible. But again, here I've only done 3 trees. And again, in a real boosted scenario, you'd probably do thousands of trees. And if you do thousands of trees, eventually you'll get good predictions, okay? But this is kind of how boosting works. And so in R, you can use the package GBM. And if I apply the same terrible settings that I say, where I say, hey, limit your boosted tree to just boosting model to have only 3 trees and use a learning rate of 0.3, our results will match the results that we got here, okay? And so here I'm going to say load up library GBM. I'm going to say, hey, fit Y based on X. Our data comes from here. We're only using 3 trees. Shrinkage factor of 0.3, and when we do that, the resulting model is boosted, and I can say, hey, what is your prediction, okay, to kind of show you that we got. So when I did it manually, I say, hey, what do you get when you plug in this value? We predict 2.267, and indeed that's what we get. When X is 1, it predicts 2.267. When X is 3, it predicts 3.172, which is what we ended up getting here. And when X is, say, 7, it's going to predict 6.147. Okay, or sorry, X is 4. When X is 4, it predicts 6.147. So these values match our manual calculations. So my hope is that at least these tables and these steps illustrate how we're getting these values, and just know that if you followed this process in, you know, to the end with say GBM, and you allow it to fit like thousands of trees, you'll actually get pretty good performance. I don't know, I included this thing. This is like, these are our predictions, which are terrible, but that's what we have, okay? So our toy boosting model is far from being done. It's a slow learner, requires, you know, a real process to run, but the point of these slides was so it's not like a complete mystery or black box as far as, you know, where are these predicted values coming from. They're found by, again, fitting tiny little trees to the residuals of the data, and you multiply those predicted values by the learning rate, and you add them to your kind of current predictions. Here, I can do boosting with tidy models, and so you can do, say, boosted tree. Here I'm using the Engine XGBoost, and here I'm going to just do it to the ozone data, okay? And so again, we have the same recipe where I'm going to impute the mean for the solar R and remove the missing values for ozone. And well, here's our workflow, and we'll fit it to our data, and this is what we get with XGBoost, and we get our different kind of predictions. Okay, and so that's what we get. Okay, and so here when we do that, we actually get pretty good performance. So here the performance, our RMSE is 3.26, and you can compare that to when we just did Ranger with the random forest all the way back here. Our RMSE was 8.24. So so as far as fitting the boosted trees versus random forest with Ranger, the boosted trees are performing better. Okay, we will wrap that up for this lecture, and thank you for your patience in as far as I goes as getting these lectures posted. All right.